Hi everyone. I hope you can hear me in the end. Welcome. I promise that I'm not going to make you suffer too much on this talk. I just want to present you the idea of analyzing CPUs. So just a little bit about Percona. Probably already heard this all day. I'm not going to stick about it. A little bit about me. I'm not going to keep bragging about myself here as well. I'm a support engineer from Percona. And a few days ago, it came an interesting case for support. Common one, most of you that deals with software already got it. It's your CPU is burning. Something is completely taking over. And in case of a database, you can't do Q-9, of course. You want to keep your services running. So the idea of this talk is to present how we support investigated this problem, how we attacked and identified the issue using flame graphs. Also, in the end, I'm going to talk a little bit about code graphs, which is another approach, and I'll explain details a little bit. So first, this slide is homage for Brandon Gregg. Not sure if all of you heard about him. He was the guru, the mentor of flame graphs. Me, I'm just a Padawan here. I'm just summarizing the things. But his content, it's much more broad than what I'm going to show here. So, what are flame graphs? The best way to define flame graphs is using the words of the creator. So basically, flame graphs are a way to visualize the profiled software. And in this way, we can quickly identify what are the threads running, what code paths are running on the CPU. So, saying that, let's be a little bit more specific. And what is a code path? Most of you are aware of. This is a really simple code. Most of you saw it all in universities or doing your work. Main function, some functions that are called during the process, and this will lead us to call chains. So what are call chains? Call chains are possible ways that the functions can work based on the behavior of the user or the behavior of the database. So in this example that I showed before, which is like possible library software, what we are doing? Getting book lists, getting the book and the author, or the editorial, or getting a print, whatever. These are possible call chains that can happen of your tree. Of course that we are talking when the software is running fine, not when he has a bug and it crashes in the middle. Saying that, we have the possible call chains. What do we do? So we profile it. So what is profiling? Profiling is a way of capturing metrics for a constant period of time, and then we can aggregate and combine and analyze it later. So there are several ways of profiling. Most of you already use it without knowing the name. Raise your hand who never got the issue from the developer, like, look, my query is slow. What do? You enable the slow log, then you set the long query time that you want, and then the queries are going to be profiled in the slow log. This is profiling as well. And later you use some tool that you want, PT query digest, grep, whatever, You aggregate the queries, identify the ones that are using more rows, consuming more time. You use the metric that you want. So this is a profiling, a SQL profiling. In this case, I want to profile stack traces and code paths. And for it, to analyze the burning phase, we are going to use perf. Perf is widely used on Linux. I think most of the installations comes by default with perf. If not, it's a really simple install, a yum, and you can install it. So with three simple commands, you can create the SVG file. And what perf record do? -A means that we are going to profile all the CPUs, and -G, we are going to capture call graphs or stack traces. -F99 means the frequency, so we are profiling the CPUs at 99 Hertz. And -P, this is the little trick, so you don't have to do PS and get the PID every time. If you're running a single instance, of course. If you have multiple ones, then this is not going to work. And we are going to profile this for 1 minute. We are going to create data for 1 minute. After that, we are going to make this machine readable, using perf script and sending it to the output. And finally, using the tool provided by Brandon, we are going to create the flame graphs. Now, let me show you the flame graphs itself. So this is a flame graph. Basically, this is the data that we profiled using perf, and after creating the SVG. So this is interactive, so you can zoom in and zoom out. I'm going to show you for the analysis. It's a little bit. So how do we identify, how do we work with this bunch of colors and data? So you have the y-axis and the x-axis, and when we are analyzing on the vertical thing, you are going to see several stack traces. We have more above, but I'm not going in details. Let's suppose this is the last one. So the last one is the one that is current on the CPU, and the other ones are its ancestors. So the best way to read is bottom up. So because I profiled MySQL process, sorry guys, you're in the end maybe may not see, but we can see that 100% of the CPU time was spent on MySQL. Why? Because we were perfing only MySQL. Now, when we look on the x-axis, the order from left to right, it doesn't matter. Like, this has no logical order of time. It's only sorted in an alphabetical order. And why? To maximize the aggregation. That's it. There is no more meaning from left to right. But when we are talking about the size, the width of these boxes, this is what matters, and this is what we are going to analyze. So as larger becomes the box, more CPU was spent on this process. And here comes the good thing. This was based on a real case. So if we start, MySQL is using 100%, but when we come to this outer table, we can see that 54% of the sample that we got was spent on the outer table, which is interesting. So when we go deep and we zoom in, we can see that now we have only the stack trace for it, we have the functions that MySQL is calling. And these bars starts to be constant. And we see copying data, insert on secondary index, and now we see we are spending a lot of time checking foreign constraints. After that, we are seeing freeze on data dictionary, and this requires a little bit of understanding the code, but this function means that we tried to acquire the lock here, but we couldn't, so the process is spinning, so it's waiting. And after investigating, we collected some interesting data, and we identified that because we are checking foreign constraints, and the database of this customer had a small table open cache, we saw several tables being opened and closed. So this has a high cost for MySQL. Our proposal was increasing table open cache, and with that we could reduce the size of this, and it was smaller than the CPU, not that stopped burning, this is like a common name, but we made this whole process more friendly for the CPU, and the database could go on more smoothly. So this is the real importance that we evaluate for flame graphs. So, moving on, I'm going to talk a bit about code graphs. So what is code graphs? Basically is what we call off-CPU analysis. So if the previous flame graph was analyzing and identifying what was running on the CPU, code off-CPU analysis and code graphs identifies what is making the thread wait to be executed. So we have the both sides. And in the end, I'm going to talk how do we merge them. So off-CPU analysis is where we are spending time waiting for things. As we can see on this graph, flame graphs are responsible for these two things. And with off-CPU analysis, we can identify why your query is waiting. If the query is waiting for disk, if the query is waiting for, the thread is waiting for disk, network, or in case of MySQL, we know that there are several locks. If the default isolation level is repeatable read, so if you are inserting or updating, you have the famous and infamous gap lock, so this might make the thread wait, and this is all part of the off-CPU analysis. How do we do it? This is made with BCC tools. For kernels that are newer than 4.1, you can just install it. It comes already with the operating system. I just pasted for my opinion, the most two common ones, Red Hat, CentOS version, just a yum install, or Ubuntu Debian, the apt-get install, BCC tools, and then it's going to install it for you. A way to validate, just check if this directory has the tools, and you are going to see, if you are more curious about, hundreds of scripts. You can do profiling with BCC tools for disk latency, network, every sort of things. This would take a life to learn. There are much better people than me about it. But the one that I want to focus now is the off-CPU time. So with off-CPU time, the -D option will put a delimiter. This is for the parsing of the stack trace. F is to make the stack traces folded. Minus P again is for identify the PID of the process. And we are going to collect for 30 seconds. The same idea, we are going to produce the stacks. And here we can use the tools from Brandon again to create the SVG files. So let me quickly show to you. So this is the code graphs, and this is extracted from a MySQL that I just put it up, and it was idle. There were no queries running on it. Then I run a test with the classic sysbench, of course, and this is what is happening when the system starts to get saturated. And as we can see here, we are spending a lot of time handling connections, and this is waiting for read or writes on the I/O socket. But the curious thing, and I did this on purpose, of course, my MySQL, I put very limited resources on a single core virtual machine, is that I was opening and closing connections for every single thing during my workload. One proposal here, after we analyze it, maybe using connection pool on the application or use thread pooling on MySQL side to reduce the amount of time spent opening connections. And to resume, of course, this, not only this, but the flame graphs, they are absolute numbers. So it's interesting when you collect both, and on this way you have the 100% picture of what the threads are doing and waiting, and then you can correlate everything. Because just taking a look at this, you can't infer if your MySQL is suffering or not. So it's good to have both sides of the story, the running one and the blocked one. That's it. That's it. If you have any questions, I am available. Sorry for being short. I hope you got the idea. We are going to talk more about this on Percona Live, or you can catch me around here taking a beer. I will be really glad to answer all your questions. Thank you.
We have time to take some questions now.
Okay, so if someone has questions, I am available. Yes?
I was, as a new tool for me, it looks very impressive. I was surprised that it was how readable the calls were in the stack. Is that, it doesn't look like you did any special compile.
No. Can you repeat the question? Okay. Sorry. So his question was if I did anything special to MySQL to analyze the code paths. For the MySQL community version, there is a package for RPMs, the debug package, which install the symbols. So like you just need to, if you do the bundle installation, it will come everything. So you don't need to compile anything special to analyze it. Yeah, like no magic, just another RPM of the bundle.
Comes from the names of the function calls and things. You can sort of understand what they mean and what's going on, and therefore you can actually understand from that. I guess that's the communication. That namings are good, and therefore it helps to figure out what's going on.
Yeah. Another thing that I usually do, I get on GitHub of MySQL, for example, I have on my repository, then I go to the source code and open the function when I don't know, and the function is really well documented on the header. It's really easy to...
My question was actually going to go, I was going a little bit further, but that's all good, that's what I was saying. But my question was more actually, I mean, most of my time I'm working with Oracle and Postgres, and I know Oracle deliberately obscure their function calls, so people can't unpick what they do. I read the dislike about Oracle, but that's how it works. But actually, a lot of the time I'm working with Postgres, and also I'm getting MariaDB. It has the same name convention. Is that right? Or?
I'm not sure because Maria on recent versions are going to the left and MySQL is going to the right. Like they are not. But in the past, the functions were crossed, like most 99%. Nowadays, they are really starting to differ.
Okay, and you presumably have no idea about Postgres, whether it's nicely labeled in that way. I know Oracle's deliberately obscure it.
I can check for you, but for Postgres, I don't have. Sorry.
So for the CPU measurements, is there a way to see what line it is in this function when it's off CPU? Where it was blocked and do not able to continue? Or do you only get the name of the function?
Sorry.
So you at one point a process is running and then it does something that makes it block.
Mm-hmm.
And it becomes off CPU.
Yes.
But what you show, I think, is only the function names. Function that's happened. There's some way to actually see which line or area of the function that is occurred?
No. Then you have to investigate the source code and, like, for go to the specific line, you can use GDB. But then this, like, GDB is attached to the process, and then you can literally dive into the codes and every single line of. But this brings a lot of overhead, so we don't use on production. But it's an option.
If you don't have shell access to the box like managed service, is it possible to do anything from the MySQL command line for flame graphs?
No, because these are you need the libraries behind it. Well, I think that's it. Thank you, guys.